That's amazing. So many people in here want to talk about cryptography. That's interesting. So what we're doing today is we're talking a bit about hardware security modules. And the first question I always hear is about what is an HSM and what do we do with these boxes. So the idea behind HSMs is that we protect keys in hardware. That means that key cannot be copied. Here, the keys represent a value that we want to protect with them. And therefore, it's really important that we do not share resources, because sharing resources is always a risk, whatever you do, because probably keys get copied, you have keys in backups, you have things around. So you should always isolate keys and secrets. And another fact that is really important is randomness. What most people don't know is that cryptographic key, when it gets generated, it's really, really important that a key is really random. So it's like in a football match, if you know where the ball will hit the next man or some other destination, it isn't that fun anymore, and it's the same in cryptography, so the key must be completely random, like a football on the field, to make sure that the key is really secret. And rand in C, for example, is not random. So in the cryptography, we call it entropy. So rand does not provide the entropy to make sure that the key is really, let's say, random. So what are HSMs? All of us have HSMs in the pocket. So we have different types of HSM. We all know, let's say, the smart cards. So each smart card we have, so each credit card is an HSM. So the HSM itself protects the key inside, generates the key inside, and can never leave the box. So especially for digital passports, you may have Austrian Bürgerkarte, for example, or something like this. The key is inside the card generated and can never leave the card. We have secure elements like TPMs, we know from our computing environments, or that should be in embedded devices, and we have the data center HSM. Because the world runs on crypto, that means all our banking account stuff is protected by HSMs, which are made for the data center stuff. So what is this special by HSM, especially when we talk about data center HSM, is that HSMs enforce policies and roles inside. So the key itself isn't just stored in the box, so we have a lot of encryptions keys around, like an onion ring, which represents roles and responsibilities inside a box, like a security officer, like a crypto officer, stuff around that, to make sure that, let's say, organizational requirements on key protection can be technically ensured. And another thing that is important is we can separate each application from each other and make sure that we have the possibility to separate keys, let's say, from applications and different use cases. So multi-tenancy, for example, different departments, and each of the partitions can have their own roles and usabilities, and therefore we can use one box for many different use cases. So how do we interface with these boxes? So there is a standard outside when we have our application on the top. We have PKSS 11 usually. I'm not sure if you heard about that. If you do a bit about crypto, you have probably heard that. That's the standard. And underneath there is a library, DLL or SO for Linux or whatever. And then we have the hardware, the smart card reader, and then we have the box itself. So we all know there are standards, and there is Microsoft. For Windows, there's a different way to access boxes. You can use PKSS 11, but for Windows applications, Crypto API is the standard. So whatever Microsoft's using, so Microsoft PKI, whatever, they rely on the Crypto API on a mini drive and KSP. Please keep in mind these Crypto API will be important for the stuff we're doing later on. And whenever I talk about HSMs, so I do cryptography for a lot of years now, is that people saying, I don't need HSMs, I'm fully protected, I'm fine with that. And I thought about what should I tell you today about HSMs, and I thought this is a security conference, I think it's not that funny if I tell you a bit about HSM. I said I would tell you how you can ruin your day with just about 5 kilobytes. So the setup I'm showing you is, it's a standard server setup. So what we see in all environments. So this is not special for this talk, this is what I see in most of the customers I'm working with. We have a default OS setup, Windows Server 2016 for example, with a Microsoft C installed with the base CSP. CA is really important nowadays because when we talk about Office 365, when we talk about, let's say, interaction with cloud services, a PKI is a requirement. And for some cloud tools, to make them seamless integrate in the network, CA is really great. Microsoft offers a very cool CA solution inside the operating system, which is the #1 deployed outside. And we use it in standard setup. There are Microsoft white papers and stuff around how you can do this. It's click, click, finish, and you can move on. We have used 4K RSA keys without 256 to be compliant with any outside services to make it fine. We have a root CA installed, and it's an enterprise CA on a domain joined computer. So what I'd like to show you now is that we switch on the server, having a look a bit around that and see what we can do with the key, and give you a bit of information how I can extract the key and what maybe happen when the key, these are, by the way, are the 5 kilobytes, gonna go in a wrong direction. So I've installed a standard server 2016 here. And we have the standard Microsoft CI. You find it in the, let's say, toolkit section, and starting the interface from Microsoft CI. So it's easy running. We can go on the properties here and go down. You see all the issued certificates and stuff like that, and we see the CA certificate in the middle here. You see it's a Microsoft software key storage provider, and it's SHA-256. We can have a look at the certificate. We see the validity. We see the attributes of certificate, including the serial number, which will become important for us later on. And we can, let's say, see on the path that's the root CA only. So that's a complete standard setup. Hope you agree with me. And I now save the public key to a file we put outside. This is an important step after the setup, because on Linux systems that doesn't do it automatically. We need to insert a certificate in a trusted store. And then we are fine to go, but we cannot export a private key. But the private key is not in this interface. We need to know that Microsoft CA runs as a system service. So in Microsoft Windows NT or Windows Server, the system service, the system account is the computer account. So we need to access the computer account certificate store now. We can do over the Microsoft Management Console. There's a CA snap-in. And with this snap-in, we can easily, let's say, load the certificate snap-in, and then we can select if we want to, for a service account, for computer account, or let's say for a computer account, accessing, let's say, the stores. These are 3 different stores. And what we see here is a very interesting thing, because what we see here is that we can also connect on another computer, which is really funny, because if our PC is, let's say, enabled, and you have disabled Windows Firewall, then administrator can connect to a CA server, even if interactive logon is disabled. Keep that in mind, just for now. So we see the personal store, we see there's a certificate in. In our example, it's easy, but we double check with the public key if the serial number is the same. It is, very good. And we can easily export now the private key, so public and private key. This is intended, this is not a fault by Microsoft, it's intended the first time that gives you the way to back up your key, because you need to back up it once to make sure the key is stored somewhere. We do it now. We can define a password to protect the P12 file we're exporting now. Very easy thing. Put it on the desktop to put it aside. And then Microsoft recommends delete the certificate in the store and re-importing it, but these times do not allow re-export by setting the ACL. The ACL can only be set during import. So we have the 2 files on the desktop. Now we delete the key here in the manager and saying, let's re-import a key. So doing that. Key is now gone. And now we click and right click and say we import. And what we can see now at the import is that after selecting the file, which is a P12, so you have to search for containers, that we have here this small button here, which says make the key not exportable. If this flag is disabled, key export is not longer allowed, so Microsoft seems to protect the key. So very good, we can do this. We have re-imported the key. This is based on some white papers you can find on the internet, also in MSDN. They click on the right click here, and now we see if we export a key now, the key cannot be exported because it is grayed out. Yeah, you can see it here. No way to export a key. So far so good, the key seems to be protected, and most customers stopping here now and saying, hey, that's fine. Let's try another thing, we disable the key. And I've installed a small little tool, probably some people of you know. It was famous for golden Kerberos tickets, but we can use it here. It's called Mimikatz. I think you know it. And what we do with it, we just go to Microsoft, to Windows debug mode, and we patch now the CNG key isolation service in memory. So that's an easy thing. So we can just say here, are exporting the key. And now we can say crypto API is now patched in memory, so it does not on permanent stuff on the hard drive. After reboot, it's fine again. And now we can easily export a key. What we're doing now is we're exporting the keys directly from the Microsoft Certificate Store to our folder where we've run the tool to. The password is Mimikatz, so private and public key is exported again. Yeah, you have the keys in here. So what exactly can you do with the keys? Most customers saying now, hey, I'm fine. I've just installed it for web server certificates, just for Office. I'm completely fine. It's not a problem. I do not use CA for a lot of things, just for my web servers in the intranet. Really? Let's see. Let's go move on a client. We have a default OS setup, no special settings, with Windows 10. 1803, so it's a standard Windows 10 version, professional, a domain joined computer with OpenSSL for Windows installed, and secure boot is activated. By the way, secure boot is a requirement for getting computers Windows certified, so all modern laptops have a TPM with secure boot completely activated. So what we do now here is, I just log on with my computer account, and let's say just copy the file on the desktop. So very easy, I'm logged in, I'm a standard user. I have no special rights in the domain, I just copy the certificate in here. Let's rename it a bit because I don't like this name here. And then I've provided a small little script that runs completely offline, no connect to the domain. Yeah, it's just in the folder here I've prepared, which use only Windows services. So we only use OpenSSL and some Windows-based components. When we run the tool now, it generates a Microsoft Virtual Smart Cards. It's a TPM. For people that know it, it's TPM SVC, which using it. So we can create a virtual smart card on the TPM chip. And it's asking me now if I want to create a certificate for a user. I say, yes, Bob. Windows is asking me for the smart card credentials. I can move it in. Then the next question is, would I like to add an additional user? Yes, of course. I'd like to get a certificate for Alice as well. And when we do this, we need to enter the smart card pin again. For our TPM, it's 1, 2, 3, 4, 5, 6, 7, 8. No additional user, and now we log off. So a very easy thing. When we log off now on the Windows, then we have some fancy thing on our login screen, because now, if we're signing out, we see login options here, sign-in options here. These sign-in options are new. And when we click on here, we have a virtual certificate for Bob and for Alice. And now we can log in with their credentials by using our own PIN we have just defined. So why the hell can we just take a web server signing CA from an Active Directory, copy a certificate out of it, and log in with a completely different username? First of all, we need to understand a bit what does it mean to have login certificates for Microsoft. So Microsoft login certificates means that we have a certificate in the end-to-auth store in Active Directory. There's a special area in the Active Directory where all trusted login certificates are in. The digital signature is a key usage requirement, and smart card logon is extended key usage defined. So these are special attributes in the certificate. And the user principal name has to be set as an UPN in the thing. And here is an example for OpenSSL, very easy. Very funny is that OpenSSL has the OIDs that we need to use already included, so Microsoft Smart Card login is already in here. That's completely fine. So we can just put these data, put it in, and use it. The NT-auth store is a bit special because the Microsoft CA, when we install it as an enterprise-grade CA, will automatically provision the certificate in the NT-auth store. Without knowing that fact, you have enabled Microsoft Smart Card Logon domain-wide in the domain you installed the CA by just having the certificate. What is the problem now? Secure boot requires installed TPM, and the TPM is a prerequisite micro smart card, virtual smart card. It means that all modern notebooks have the ability, without buying additional hardware, don't have to buy smart cards or token or whatever. It's installed. Use your computer, a small tool, TPM, VSC, or Google for Microsoft Virtual Smart Card, you can use it. Also for logon stuff you'd like to do, you can use it also for other certificates. It's then in the TPM installed, and it's ready to be used with a PIN you define like a standard smart card. That means all required certificates are automatically deployed. This is also interesting because the policy inside the default setup means that we distribute everything's necessary on the domain controller, on the clients. You just have to install the CA, wait for, let's say, minimum a day or whatever, and then all clients have the prerequisites. This is also default for CA I just want to use for web server because I have no idea what's going on in the background. And 90% of installed CAs are enterprise CAs. Even if no smart card login is used, the certificate is still in the auth. And the biggest problem you have now is, now that this feature is in, you now have ghost certificates in your network. What is a ghost? A ghost means, because I've created certificates completely offline from everything else, I don't know the serial number, so I cannot put it on a revocation list, so I cannot revoke the certificates, and I don't know that these certificates exist because I don't have it in the inventory. So the only chance to move around this is that you rekey your CA completely. So if you really want to work with a CA and you just use it for web server, please keep in mind that you have to look at NT-auth store and make sure that the certificate is not in. But the best option is that you use some HSMs. There are different HSMs in the market from different vendors for different purposes, USB, smart card, whatever. We can do whatever we do. And there are also cloud solutions out in the field from very prominent vendors. I just moved Depot around. We have some experts here in the room as well for this. So there is a solution. But please keep in mind, protecting your key is important. This is just one very easy example how you can ruin your day with just 5 kilobytes of data. It's just a public certificate, and usually nobody really knows about what it means if it's in your network. The next thing is beyond the IT world. So what happens with the new era when we talk about industrial IoT and Industry 4.0? What does it mean for this? So I know that it is very cool if you have smart bulbs in your area, if you can control the stuff from your mobile phone and things like that. But what's about security in this? We know it from the press. Here are some examples from Germany, that we have some troubles with smart TVs and stuff like this. But the attack vendor really changed, and this is what I'd like to give you on the way, because the attack vector changes when you hand something over to your client. I'm not sure if you know these little, let's say, baggage stuff here. It's an, I lost the name. It's TSA lock, for example, for America. So when you travel around, you have these TSA locks with really protected keys. I have the keys. I've printed them with a 3D printer because somebody took some photos on the airport, created 3D models, and uploaded on GitHub. So if you lost your PIN code for your bag, just Google for, let's say, TSA keys in GitHub, and you will get the keys. Just download it, print it. You have to play around with your printer, but it can unlock my baggages very well. So what do we do now? Because the keys get compromised, and I cannot change the locks now on my devices because I don't have access to them anymore. I don't know who bought these bags. I don't know where these bags has been sold to. So even if I try everything I can do, there are still bags out in the field that where I have access to with my keys. And the thing is that these keys are now part of your network, and you have a complete different target now where you're thinking about. Have you ever thought about firmware you install or you upgrade on these smart bulbs or light bulbs and things like that? A lot of people now saying we have protected because we have disabled all ports or access to our hardware, and this is not the truth. I'd like to put you a bit away from IT and give you an insight about what it means when you listen for keys and common crypto algorithms we're using today. So let's assume we have a microprocessor around and we have a look inside such a processor. It is not limited to IoT, it also works for IT applications, for IT processors, and it's independent from the operating system, because we only look about a hardware now. So this is how a microprocessor looks inside. We have different areas here, algorithmic logical units, memories, caches, and so on. We go in, and a bit more, and a bit more. And these small points we see here are transistors. These are small little transistors. That means the microcontroller contains a lot of transistors which only draw current. That means they take power when they switch from 0 to 1. This is really funny. So let's have the Ohm's law in action. I'm not sure if you well know about how resistors and current and power and things going on. But there's a microcontroller with a power supply outside. VCC is our power supply plus, so let's see 5 volt or 3.3 volt, and we have a resistor next to the connector on the microcontroller. We know there is a current flowing on inside the controller, and we know that over the resistor there's a downfall on the voltage, and we just taken a probe exactly next to this resistor here, which is UP1, and we can do some calculations here. I try to avoid math as much as possible. And by the way, with the Ohm's law, I is U through R, we can then calculate the currents flowing through this resistor. We just take an oscilloscope and having a look at this. The following examples are based on a standard ARM Cortex machine we use very well and very often in industrial applications and in IoT devices. Really standard thing, you can buy it from different vendors. It doesn't matter what you take, the architecture is the same. And we have a look in the manual. We know about some assembler codes that we have in, and we know what kind of operations take how many CPU cycles. So let's say from 1 to 12, everything's possible. So what I'm doing now is, I just show you a bit of a source code in C. I hope it's really easy. We're just running a while loop now, for example, and having a look in the current drawing from the CPU. We see it's pretty much harmonic because we're just doing a loop. Let's count to 5. So we set a trigger on high, and then we count, and then set the trigger to low. It is like this in oscilloscope. Now we put some RF filters in. And what we can now see is 1, 2, 3, 4, 5. So we know how that we've counted up to 5. Let's do it for 7. Same thing, filter. And we have 7 counts plus. Do a multiplication now. Same thing. We've multiplied 11 times. I can now see that's a different signature in the screen. I can, let's say, divide. Same things going on. And now what we do is, because we've seen that, let's say, multiply and count having the same CPU cycle, so we cannot think about a time. So we need to move in, and now we say, hey, count, multiply, and divide probably have the same CPU cycles used, but they draw different power. So the amplitude represents the power we've used. So by measuring the power the CPU takes from operation, we can gather it's an count, multiply, divide operation. And we know about the differences here. And then when we're talking about RSA, we know that RSA encryption means that a ciphertext, it's really easy, is the text, the clear text, power to E, modulo n, and the decryption means that, let's say, the message is the ciphertext to power of D modulo n. And we know now that E is the public key, the public exponent, and D is the private key. And N is, let's say, standardized value. You can usually use 3, 5, 17, 257, or 65,000 something. So it's a standard thing you can try around. So with just measuring the current, we can go back to the RSA keys. So RSA is using numeric calculation, so it's really easy to get into the keys. But what's with AES now? What mainly used to encrypt firmware and stuff like this? AES is a block-based cipher that uses logic operations combined with a substitution table we call SBox. What does this mean now? So in AES 128, we have a message, we have a key, and we have a ciphertext. So if you have a 128-bit key, 16 bytes of message code, then we receive a 16-byte, put in a 60 byte of message, we receive 16 byte of, let's say, ciphertext. When you use the ACB modes, electronic codebook mode, which is a standard for most of these devices, then we always do the same. Block 1, 16 byte encryption. Block 2, 16 byte encryption. Block 3, 16 byte encryption. So now it's not that easy to get into the keys because it's not longer numeric operation. But we know the AES algorithm. We know it. And we know that when we use one of these bytes to encrypt, the following happens. we do an XOR with the key byte, and then we do a substitution in the S box, and then we do something else. That's not long important, because after the S box, this is our attack surface. And we want to see what's going on here. So what we're doing is now, we know the S box. This is standard for AES. You can Google for it. It doesn't matter. Yeah, you can grab it everywhere you like. And we have a look on the oscilloscope, and you see exactly here about what's going on the oscilloscope. So how long does it take? Here we see the different power signatures here, what's going on. And we know when we do encryption, we have different data lines that runs data through, going from 0 to 1. And what we know now is, when we put all these data lines together, what we see when we take the main power of the CPU is that the Hamming weight for each CPU cycle represents, let's say, the power consumption of the device. So the Hamming weight is the number of bits set to 1 in a number. So if we have a byte and we have 5 ones, so it's 1, 0, 1, 1, whatever, we count the ones, and this is the Hamming weight. So very easy. And the power is so direct proportional to the Hamming weight. That's really cool, because now we can start a DPA attack. So we try different input data, get them on an oscilloscope, and we see that for all of the input data, we have different power drawings here. So these oscilloscope, let's say, lines represent what I'm doing here. So what I'm doing is, I'm just taking some input data. I can decide what I use. For example, bootloader, I use some predefined input, and I suppose a key. It's always 0 in the thing. We do XOR, then we search in the S box for the first thing. D6, interesting. So let's go in the S box. D6, it's F6. Replace it to F6, convert it to binary, count the number once. Same for the next. Okay, A0, 04, 49. Replace it, count the number once, and then we do it for the rest. Now we do the same for supposed key 0, 1, 2, 3, whatever, till we finalized 0 to FF. We do it again, and do it again, do it again. And then we can do the attack, because now we know the Hamming weight for the point in time we're doing the attack. That means that the Hamming weight is related to the power consumption here, and which means that we can now put our assumption and see if it correlates with the data we've taken from the device. So a short mathematical outcome, what is correlation? We're searching for linear correlation. These are some examples about 1 to 0, what correlates. We're searching for linear correlation of our data and taking the best assumption that correlates best with the data we have. So how do we calculate this? Let's do some mathematics. No, that's a joke. We don't do mathematics. We let the computer do this stuff for you. So we now compare the Hamming weight of our assumptions, as I said before. And let's have a look which assumption is the right. So we see for the first, probably 6 is very good. For the second, probably 2 is very good. You just see the point in time over here. So when we see here, here's a point in time 1, 2, 3, and we just correlate the data next to it. So at the very end, we can compare the possibilities. And the cool thing is now, for AES with a 128-bit key, we have 3.4 multiply with 10 to the power of 38. I don't know what this kind of number is called. But anyway, too far, let's say, possibilities we can try. But with DPA, we now calm it down by 2 to the power of 8. It's 256. When you have 16-bit keys, 4,906 bits per key. And because we're doing oscilloscopy on the power, we need to count in points the oscilloscope takes. Let's make 5,000 points. That's enough. So we have 20 million possibilities. Even my small computer here on the desk can do it, let's say, in about 5 seconds, and we can analyze the correlation in 21 seconds. So this is the example. We having a look about that. So we taken the traces, did it for the key assumptions. So we have, let's say, 256 traces. We take the points into our things, and then we're doing a key guess, and we can calculate the correlation. If you have a look in here, you see the first line. This is the cryptographic key, and you see the correlation is the highest in the table. Okay, for the keys we have put into. So at the very end, we can do a data plot. What we see here is, this is the key is not matching. That's the green line above here. In the middle, we have the key that's matching, and then we have the green line underneath. And what we see here, this is exactly where the substitution is happening. And if you count it, these are exactly 16 spikes. So it's very easy to get her out because we know the algorithm, we know how it's working, we know the mathematics and the power drawings. If we want to make it a bit better, we can now do a partitional guessing entropy calculation on the data. It doesn't matter what it means in detail, but we can, let's say, make the thing better, because we can calculate from the data we have that 30 points, so 30 traces are completely enough. We don't have to do hundreds or 200s or 500s, it's just about 30. For the next attack, we can do it in an optimized way, because we can just step in here and see about 30 traces should be enough. So at the very end, it means that never implement crypto in software, because when you want to do crypto in software, any device, it doesn't matter if it's a Windows, Linux, or whatever based computer, if you require performance and security, you can only, let's say, you do performance on the stuff, but then it's easy to calculate the stuff, because on very, let's say, optimal implementation is very easy to go and go back. And if you want to make security, you cannot have performance that much. So the best thing is, let's do it outside in a secure element of your choice to make sure that keys needs to lie in hardware. And please think about security before you start the project, because that means you have to add additional hardware in your design, or you have to put HSM in your data center before you're starting. Do it afterwards doesn't really make sense. I have one example here from a device we've seen so far, we'd like to use for a project, and they had a look at the release notes, and there was some interesting thing in. And the firmware release 2.2, we've seen the following passes. That says new features, modified firmware structure for security purposes, please upgrade to version 1 before upgrading to 2. So I was a bit surprised about 1.11, what does it mean? And you click on the next thing and you see in the release notes, version 1.11 says support accept encrypted firmware for 2.0 and above. A colleague brought me this and said, hey, that's an interesting thing. Can you tell me what this means? And then I had a chat with him and said, I don't know what it's going on. And the interesting thing is, it must be clear that the key for version 2 and above must be in version 1.11. So if you have some ideas about reverse engineering, we can discuss it outside if you'd like, how it reversed. The extraction of key took about 10 minutes. It was really easy. Yeah, and you can do it fully with open source tools and Linux, very, very good. Or secure hard drives out in the field, really funny, because most of these implementations are also very, very weak, because you can do a timing attack on this. Just, let's say, count the time you enter the wrong pin versus you enter the right ones. And then you can grab out by just counting the time between pressing the enter key and the light goes on. So at the very end, what I like to tell you a bit is about that keys in hardware is always good. You have a reliable service outside that is probably tested against these attacks, but please have a look in the manual if that's really the truth. And you can be sure that the crypto algorithms are implemented the right way. There are certifications for this process to make sure that an AES implementation really works for all ciphertexts, not for about some. And then to make sure that all your keys are created in a secure way by having a true random number generator. So keep keys in hardware, take care about keys in hardware. If you'd like to see such HSM in action, you can visit us at a booth. I've taken some with me for people never seen an HSM. It looks like a standard server. You can plug it into your computers, whatever you do. And for industrial applications, stuff like this, there are different stuffs around. If you have any questions about keys in hardware, whatever, I'm happy to assist. And therefore, I'd like to say thank you for taking the time and going a bit in a deep mathematical stuff. I know it's hard in the evening, but hope you enjoyed it. Because,
Any questions? Where in the Active Directory can you check for Microsoft Enterprise CAs that are active for the domain?
That is really easy to do. You can use a small tool called CertView MSC. This small little tool is a snap-in which checks your CA. It's a really useful tool if you check if CRLs are fine and stuff like this. And if you right-click on the directory, go to Properties, and then you see the NT-Auth store. Or you can go in the config partition in the root domain, just under NT-Auth store. It's in the root target. So if you like to use ADSI edit, you can do it as well. Certview.msc. on the Windows server, when the CA is installed, it should be installed as well. So just press Windows R, enter, and then you're in.
Further questions? And thanks again, and you're probably available outside for
I'm
further
available at the
questions.
booth if you want to discuss something more. Thank you, bye-bye.